All right, everyone. So today we have the second video on covering spaces. On the first one, we discussed basically a couple of examples. So covering spaces of S1, which you should be quite familiar with at this point, and covering spaces of the wedge of two two circles. And hopefully that gave you a feeling already for what the topic is. Our plan today is to basically start developing the theory a bit more rigorously, and we are basically gonna go back to an idea we saw already for S1. And what is the idea? The idea is that, well, when we were looking at S1, and I mean this is still true now, we are really interested in understanding pi 1. Alright, so as such, we're interested in maps of S1 into a topological space, right? And the idea we followed back then was to say, well, look, I want to study loops in S1, so what I do is I lift them up to R, and then, well, I do manipulations there, right? And basically the big result was like, well, the way in which we measure how much a loop is turning in S1 is by measuring where its endpoint in R ends up, the endpoint of the lift. So basically, yeah, so let's do exactly the same. Let's develop the notion of lift in general. So how does this go? The situation is as follows. So I have a basis space X and a covering space X tilde on top. I have a map from Y, some other topological space, into X. And what is a lift? Then a lift, F tilde, is basically a map from Y into X tilde such that this diagram commutes. Right, so it's the same doing F as doing F tilde first and then projecting down. Alright, so basically the last result of this lecture will be about a general criterion for saying when do lifts exist. But the first step is the following theorem, which says that, okay, I don't know how to lift F, let's say, by itself, but if I have a homotopy of things and I know how to lift the first one, then I can lift the whole homotopy. How does this work? So let me go over the diagram here. So let's say I have a homotopy of maps Ft that goes from Y to X. And here I write big F, and big F is the anchoring of this homotopy. So big F is a map from Y times the interval into X. And it's a continuous map, right? Because this is a homotopy. Now, I want to lift F, and I'm given an extra piece of data, which is a map F tilde 0 that is a lift already of F0. All right? So again, I don't know how to lift arbitrary maps yet, and in fact you won't be able to do it in general, as we shall see. But if you lift the first one in the homotopy, then you can lift all the others, and this is what it says. The statement says there's a unique F, a big F tilde that basically makes this diagram commute. So basically it lifts big F and it restricts to F0 tilde at time 0, at t equal to 0. Okay. So big F tilde is the anchoring of F tilde t, which is the lift of the homotopy of t. Alright, that was a bit of a mouthful. So how do you prove this theorem? And basically the strategy we're going to follow is the same strategy we followed for R over S1. So let's recall basically what was the main idea. So when you have S1, what you can do, and what we did, is we covered it by two open sets, S1 minus the north pole and S1 minus the south pole. Each one of them is an interval. And what you can see readily is that each of these intervals, you can take their preimages. The preimages have infinitely many path components, but each path component is homeomorphic to the interval downstairs, right? And what that basically allows you to do is to say, well, every time I want to lift stuff, I can just look at the interval downstairs and identify it immediately with one of the intervals upstairs, and using this identification, I lift the stuff. All right. So maybe the motto you should take from this is that, sure, covering spaces are not, I mean, X and X tilde don't look quite the same, but at least locally they do. So if you want to lift the stuff, you should be using all the time the local homomorphisms identifying the two. Let me explain this in a bit more detail. So, all right. So here we have X, and we find some covering by opens that I call UI. Note that I'm not requiring anything about the covering. I allow to have maybe infinitely many of these opens. This is not important. All right, so we have this covering by opens, and here I have, and what I require about these opens is the following, and it's a property that we call it being evenly covered, which basically means that it behaves nicely with respect to the covering map. And it is the following. So I take UI, I take the preimage by P. Maybe here there's like many preimages, many path components, but what I require is that at least what I require is that each one of them that I call Vij are homomorphic to UI itself. All right. So yes, each preimage looks exactly the same as UI. All right. So now what do we do? So the idea of the proof is that we're gonna basically mimic what we did for S1. So like lifting, basically we know how to lift paths essentially. So what we're gonna do is basically think, well, y times 0, 1 is basically, or let's say big F is basically a family of paths parameterized by y. So basically I freeze y and I let t move, and these are then paths. So all I have to learn is how do I lift paths, and then how do I do it continuously with respect to y. Alright, so as I just said, well, let's freeze a y, and let's focus on the segment y times 0, 1. Now, since y times 0, 1 is compact, right, what I can do is the following. Basically what I do is I map the segment into X using F, and sure, there's infinitely many UIs that cover X, but due to the compactness of this interval, the following statement is true. I can find finitely many times partitioning my 0, 1 interval and a neighborhood of Y that I call N, maybe really small, such that F evaluated on N times the little intervals is contained in one of the elements of the cover that I denote by UIL. All right. Let me maybe say again how this is proven. So the way you prove this is by saying, look, I map this interval by F. I look at the UIs that cover it. I take their preimages by F. I take a finite cover. So now I know that basically it's enough to use finitely many UIs to cover this interval. And the compactness has been used. But now, I mean, since they cover the interval, in particular, they cover a small neighborhood. And this small neighborhood is what I call N. All right, that's the full proof. This is a proof we've done several times. So again, if you think this is a bit confusing, you should really maybe take a minute and think about this statement. All right, so very good. So at this point, we've chopped up our interval into smaller intervals, and we also are covering a slightly bigger neighborhood of y as well. And now what we're gonna do is sort of inductively on these intervals, we're gonna explain how to lift f, big F. All right. So at the end of the process, we'll have defined f tilde over the whole of n times 0, 1. All right. So let's go maybe to the picture, and then I will explain this statement. So here we have, maybe here is little y, here's the neighborhood n, here's the whole strip n times 0, 1. Now n times 0, 1 maybe maps like here into x. Here we see x. Here we see x tilde, and there's like 3 sheets of x tilde lying on top of x, roughly. Now the image of n times 0, 1 is covered by this UIs. This is the first one of them. And now what we observe is the following. Sure, this UI0 has many preimages, one in every sheet, but only one of them is special, and it's special in the following way. We already know how to lift y, right, by using the map f0 tilde. In particular, we know how to lift f0 tilde n, right? And well, it's somewhere, it's here. And in this open, that is the only open containing f0 tilde n, I denoted that vi0 j0. And this is sort of my favorite my favorite preimage of ey0. And now, sure, I know how to lift this tiny piece, but now it's immediate. What I can do is I can just take this whole part of n times 0, 1, and I just lift it by the homeomorphism that identifies ui0 with vi0 j0. All right, so I've defined my lift. Well done. Now, what is the thing? So let's say we've lifted up to n times t1. Well, we know that n times ti, by definition, it must be covered by ui1, right? So by the next open in the sequence. So now I just iterate the argument, right? So basically I take the next open, I choose one of its preimages, which one? The one containing the piece that I've already lifted. And now, having done that, I just continue the process. All right, so basically inductively and using always the previous step as a starting point, I just keep lifting. The formula, you can find it here. So yeah, f tilde defined over n times interval is just, you just take f and you just compose it with the homeomorphism that brings you up to your favorite preimage. All right, so the punchline of this argument is that we've defined f tilde over n times interval. And now, how do we conclude the proof? So first we make an observation, which is that, well, let's say I have about uniqueness. So let's imagine I have two of this segment. I have this segment y times 0, 1, and I have found two different lifts of it, f tilde and f tilde tilde. Well, if you just run the following process we just did, comparing them, what you will see is that f tilde and f tilde tilde must agree. And the reason for this is that what do? Well, you have here, let's say, y times 0, 1. You have it here some more or less. And now we have the two lifts. Now, both lifts must start here. They must start in vi0 j0, right? Because f0 tilde is given to us, so we have no options. But then if they agree here, they must agree all the way up to here. And now inductively, now we go to ui1. Oh, and now, well, they agree here, so they must agree over the whole lift. So the claim is that, well, my recommendation is that you sort of go over this argument and convince yourself that what we just did, in fact, shows that basically the lift is unique. And now this is enough to conclude why. So we've explained how to lift f to some f tilde defined over a tiny neighborhood n times 0, 1. Now we can do this for basically for every n neighborhood of y, for every y. So basically that means that we can define a lift in a neighborhood of each y, and that we want to claim that defines f tilde globally, and it does, right? Because these two, whenever these lifts overlap, they are of this form, and as such they agree. And since they agree, they define something globally. Right? So unique sort of, let me say that again. So we defined f tilde sort of piece by piece. These pieces overlap, but now because we know the lift must be unique, well, then these different lifts actually agree in the overlap. So therefore they define an object that is global in the whole of y. All right, hopefully you find that convincing. So out of this proof, now we can get some nice, out of this statement, we can get some nice corollaries. The first one is about paths, right? So if I take y to be just a point, then what the statement says is, well, if I'm given a path into x, and I'm given already a way of lifting its initial point, and I denote this initial point by gamma tilde of 0, then in fact I know how to lift the whole path. And therefore, yeah, I have a unique gamma tilde lifting gamma. An immediate consequence that I point out here is that if I have a loop into X, well, what's a loop? A loop is nothing but a path whose initial and final points agree. As such, I just think of it as a path, and I lift it up, and I will find a lift that is a path, but it may not be a loop. And in a second, we're going to be that, well, I mean, okay, we saw already this in the case of S1, right? So when I lift loops of S1 to R, all of them sort of open up unless they were not turning, unless they were contractible. And essentially, where they end up tells me exactly how much they were looping. All right, so we have this statement, and now this statement, there's like sort of the parametric version of this statement, which is that now if I have not just paths, but homotopies of paths, then I'm able to lift all of them and yield homotopies of lifts. All right, so let's go through some consequences of this. Basically, we're going to exploit this result to study pi1. In particular, we're going to relate how the pi1 of the covering space relates to the pi1 of the basis space. All right, so let me explain the construction, and then we'll give it a name. So, okay, so I'm interested in pi1 of the base, based at some little x, and I'm given some class there, represented by a loop gamma. Now, as we just said, I can think of gamma not as a loop, but as a path, and then I can immediately find a lift. This lift I call gamma tilde. Now, I'm not gonna get any gamma tilde, I'm gonna get a gamma tilde that starts at the point x tilde. Here I should have said that we're working in the pointed setting, so basically my basis space has a favorite base point that I denote by little x. My covering space has a favorite base point that I call little tilde x, and little tilde x maps to x by p. So now, as I said, we lift the loop gamma to loop gamma tilde starting at x tilde, and now what I can check is, sure, gamma tilde starts at x tilde, but where does it end? And this is actually gamma tilde of 1, and out of this I define a map that goes from the class of gamma to the endpoint, to the fiber over x, right? And well, sort of quite descriptively, I call this the endpoint map, but I don't think this is what it's called in Hatcher, so maybe don't use this in public, I don't know. All right, and recall this is exactly what we used for R over S1, right? Basically, studying what the endpoint is told us how much does the loop turn around this one. All right, so this is the first construction. The second construction is the following, and it's basically a way of putting together all the endpoint maps for different x tildes. So now I forget x tilde. Basically, I stop having a favorite base point, and what I do is, given gamma or the class of gamma in pi1, what I do is the following. For each x tilde in the preimages of x, we send that x tilde to the endpoint map at gamma. All right, so what I'm doing basically is, out of the class gamma, I'm defining a bijection of the fiber over x, right? Because to x tilde I send it to the endpoint of the lift. And what this tells me basically is that this group, the pi1 of the base at little x, I'm sending it to the permutations of the fiber, right? I'm sending it to all the possible bijections of this set. And this is sort of a classical thing in group theory, so given a group, you can always try to think like, how can I put it inside a permutation group? All right. Let's prove that this is a well-defined map and so on. So okay, first things first. So according to the previous two corollaries, as we've just said, this map is well-defined. Why? Well, first of all, if I have gamma, I can always lift it with the whatever initial point I want, x tilde. So this is actually a point. This is well defined. This is gamma tilde of 1. Good. Now the question is, does this depend on the homotopy class of does this depend on gamma itself? So now I have to change the representative of this class and see what happens with this endpoint. So let's do exactly that. So let's take a homotopy gamma t of gamma, a homotopy of loops. Now by the last corollary, there's a homotopy of lifts gamma tilde of t, lifting them. Of course, these are not loops anymore, these are paths. And all of them are started at x tilde. And now what I can do is say the following. Look, let's basically send the parameter t in 0, 1. Let's send it to the endpoint of gamma tilde t in the fiber. And what is the point? I mean, so first of all, so 0, 1 is okay, let me say this carefully. So since gamma tilde t is continuous, right, it's a homotopy, then that means that this map is also continuous, and I have a map that is continuous from the interval into a discrete set. And as such, this map must be constant. And that means that as I homotope my gamma t, the corresponding endpoint of gamma t tilde is not changing. So that means that this map is well defined because it only depends on the homotopy class of gamma, not on gamma itself. All right. So this ends up the proof of the first claim. Now for the second claim, what you should observe is, I mean, what is essentially this? This basically, for each x tilde, I'm basically taking the endpoint map and applying it to gamma. So as such, this is a well-defined, I mean, this is a definition, that this is perfectly legit. Because the endpoint map does not depend on gamma but on its homotopy class. It's also true that this element only depends on the homotopy class of gamma, so this is perfectly nice. So the only question about this claim is whether this is a group homomorphism. And now how do you prove it? Well, you say the following. Let's take x tilde and let's apply to it rho of the class of gamma 0. What is this? Well, I take gamma 0 tilde 0, gamma 0 tilde of 1, where gamma 0 tilde is a lift of gamma 0 starting at x tilde. All right, so I apply the first lift. Now, to apply this one, what I do is I take gamma 1 and I lift it to some gamma 1 tilde that starts at this point, at gamma 0 tilde of 1. And now, by definition, this thing I just did, it is the row of the concatenation of the two. Oh, sorry, and this should be gamma 1 and gamma 0. My bad, I'm going to change it in the notes. Give me 1 second. So I will upload them after I finish the video. But that essentially concludes our proof immediately. All right, later on, I think like in the next video, we'll probably explore this idea of seeing this as permutations and so on. But for this video, it's maybe not so important. But this we will exploit in a couple of corollaries next. The first one says the following, which is quite nice. So, well, I mean, the claim is that when I take pi1 of the covering space and I push it forward by the induced homomorphism into pi1 of the base, then this is a monomorphism. That is, this is an injective map. And why is this? It's best if we just look here to this claim. So let's look at this pi1 and let's take a class here and let's imagine that this class is mapped to x tilde itself. Then what does it mean? It means that when I take gamma and I lift it up, then gamma tilde, it starts at x tilde because I required this from the beginning. And now it also ends at x tilde by assumption. So that means that the elements that end up here at x tilde, they correspond to loops in the covering space. And conversely, if I have a loop in the covering space, what I can do is project it down, and when I lift up back again, it's like what I just said will happen, like the endpoint will be x tilde itself, because I must recover the loop I started with. So what that tells us is that inside of pi1 of the base, there sits this subgroup, it's a subgroup of those gammas whose endpoint is x tilde, and by the argument we just did, this subgroup is exactly isomorphic to the pi1 upstairs. And since these two are isomorphic, what that means is that, well, I mean, basically this map P star is just an inclusion, and as such, of course, it's injective. An exercise for you is please try to write down the details of this corollary. All right. Now for a second corollary, we're going to exploit again the same sort of argument once more, and we're going to prove some, I don't know, the other side of the coin of the previous corollary. All right, so let me go through the proof first, and then we will sort of say what the statement is out of the proof. So here again, I have the pi1 of the base, and here I'm taking the endpoint map, where the initial point I'm taking it to be x tilde. And as we've said, when I take x tilde here, the preimage is exactly this pi1 of the covering space. Now, we may ask ourselves, is the endpoint map surjective? And in general, it is not. It will. I think like some of the exercises of the sheets that I will upload have to do with this. When does this fail to be surjective? But a moment of thought tells you the following. Basically, this will fail to be surjective when x tilde is not path connected. Why? So let's suppose x tilde is path connected. This is one of the hypotheses of the corollary. So if x tilde is path connected, then if I take an element here in this fiber, let's call it x tilde tilde, then by assumption there must exist a path, gamma tilde, that connects it to x tilde, to our favorite base point. As such, this gamma tilde is a path, but because it starts at x tilde and it finishes on x tilde tilde, both of which lie over the fiber of x, then when I project it down, it will become a loop based in x, right? And now the claim, of course, is that if I take its class, by definition, the class will map by the endpoint to x tilde tilde, right? Because the lift of this is, well, it's gamma tilde again. All right, so we have this map is surjective, and the preimage of x tilde is this. So that tells me, sort of by the first isomorphism or so, or second isomorphism theorem, that the quotient of this group by this subgroup is isomorphic to this set. That tells me that this set is basically the coset of this. And now, okay, now let's read what the corollary says. So the corollary says, here I have this, the coset space, and I'm taking its cardinality. This is what you usually would call the index of this subgroup inside of this group, right? So the index. And in the other side, we have that since this set is sort of isomorphic to this set, the cardinalities are the same. But what is the cardinality of pi minus 1 of x? Well, this is just how many preimages a point has. And this is what we would call the number of sheets a bit naturally, right? For instance, let me show the picture that kind of shows into why the wording. So here, for instance, I'm showing x, and here I'm showing x tilde, and there's like 3 sheets, basically 3 copies of x, roughly, at least locally, on top of x. And of course, the number of these sheets is exactly like, you can just compute it by fixing a point in the base and counting how many preimages it has. All right, so let me go back. So that tells me that, well, the cardinality of the set, I can just call it the number of sheets of the covering space, and it's the same as the index of the subgroup, pi1 of x tilde. All right, and a corollary of this, I mean, I've written here it in blue, is that a priori, from the definition of covering space, it is not clear that the cardinality of this set doesn't change. But what we have shown is that, let me see. Yeah, I mean, we've shown that it does not, right, due to this argument. Let me continue. All right. indeed. So let's now look at some of our favorite examples before we go to one last result. All right, so our favorite example, of course, is R sitting on top of S1. And what I'm going to do is basically analyze how the endpoint map works and how this group homomorphism into permutations works. So, okay, here we have the fundamental group of the base. And this, of course, Z, right? Like like this was basically given by the number of turns, this isomorphism. So here we have the loop, well, a loop representative that turns k times. And now what the endpoint map does is what? Well, recall what this did. So if you have something that turns k times, we lift it to a path starting at 0. And if it turns k times, it will end up in the integer k. And this is exactly what it is. So this is what the endpoint map is. And now if we look at permutations, it's very similar. So again, I take the same loop representing the same class. And now what we do is we take this loop and we lift it to a path starting not at 0, but at n. And what will happen is that now this, where will this the lift end up? Well, it will end up in n plus k. So that tells me that the way in which I'm including the group Z into the permutations of the preimage, which it's also the set Z, is just as the shift. And note that, of course, I mean, Z is a big set, right? It's uncountable, so the permutations of Z is like a really big group, but pi1 is really small. It's just the shift, the shifts. All right. And here, I mean, I will make the comment in the next example as well. But what you should notice, of course, is that in this case, I mean, what is this? So the endpoint map is an isomorphism, right? Like essentially loops identified with their endpoint. And now when we think about the permutations, basically what we are doing is basically Z is acting on the permutations on Z, right? So basically the group acts on the permutations of its elements in the stupid way in which the group acts on itself. We shall see this in the next example as well. All right, so here we have x tilde sitting on top of x. What's x? X is the wedge of two circles. So here I have a vertex that I call P. So this I apologize for, it's not very nice notation because the projection is also called P, but hopefully you understand. So here we have the vertex P and we have two edges A and B. And what is x tilde? So x tilde is sort of this fractal cross thing we saw. So basically you start right, so we saw it in the previous lecture. How to say, it was like the covering space of X which was contractible, right? And it was basically you start at a vertex that you call it P0, or we also call it just the empty word. We'll just label it as empty word. And now what you do is now you get 4 vertices around it, which represent the words A, B, A minus 1, B minus 1. And now at A, let's say another 3 edges grow out of it, and they will go to the words A squared, AB, and AB minus 1. And this keeps going sort of over and over. And the main thing was that basically the CW structure we put in x tilde, basically all the vertices corresponded exactly to words, and the correspondence was simply, well, it's exactly the endpoint map. So let me explain it as such. So here we have pi1x p. This is the free group of 2 generators, A and B. And now here I have p minus 1 of the vertex, which is, as I said, it's labeled by words. And well, and basically the correspondence, the endpoint is just you take the word here of pi1, you lift it to x tilde, the endpoint will end up at some vertex, and you call that vertex w again. All right, so this provides you basically this, which is a set. It's actually isomorphic. I mean, it's bijective to this group. Very good. And now we see the same phenomenon as before. So now we have the group pi1. And how does pi1 define a permutation of the set of vertices? Well, you just do the following. So the word w acting on the vertex w tilde is you just start at the vertex W tilde and you move following the edges indicated by W. So you will end up in the vertex W tilde W. So this is again the action of essentially pi1 on the on itself. So basically just pi1 out of pi1 you produce a permutation of pi1 as a set of the elements of pi1. All right, so this is a nice example. Let's do a slightly different one. So let's go back to S1 and let's take now the covering of S1 by itself with k sheets. So this is the map essentially that takes a complex number z here and sends it to z to the k. All right, so this is a covering space. Now if I take the pi1 of the base, which I denote, this is of course z, and I think of it as a free group with one generator that I'm gonna call A. Then what is the endpoint at starting at 1, right? So here I have a mark point, the base point 1, and here I have the same base point 1. Well, what are the preimages of 1 here? So the preimages by this map are the kth roots of unity that I write in this manner, and the way in which the endpoint map works is basically it sends A to the first, let's say to the e to the 2 pi I over k, and as such it sends A to the n to e to the 2 pi I n over k. All right, so basically you move n kth roots of unity around. Now you should compare this to what we did in the previous video because it's exactly the same. Now for the permutations, it's very similar. So you have all the preimages, and how does an act on the kth root of unity? Well, it just basically adds. Yeah, it turns n kths around. It turns it by n over k. All right, and lastly, here we have the group, the fundamental group of the covering space. So I denote it differently. I denote it as being freely generated by B, and what will happen, how the way in which it maps to the fundamental group of the base is by mapping B to A to the K. As such, the image subgroup is the subgroup generated by A to the K. And here we see already, for instance, an instance of what we said here. So what is the index of the subgroup generated by A to the K inside of K? Well, the index is exactly K, right? And how many preimages does the element 1 have? Well, it has K preimages, the kth roots of unity. So it works. All right, so these are all the examples. The exercises from the sheets, some of them will be about this, but you should most definitely, try to go over the examples of graphs in Hatcher, start looking at the exercises from section 1.3 and so on. All right, try to become familiar. If you play around with this, it will be quite easy, I think. There's no reason to be afraid. It's kind of very intuitive things once you've played with them a bit. So let's finish the video. Let me see how are we doing time-wise. Yeah, so let's finish the video looking at the result I promised in the beginning. We call this the lifting criterion. What does the lifting criterion say? So it says, sure, before we explain how we lift homotopies, but assuming we had already lifted the first map in the homotopy. So now the question is, okay, if you give me any map, f from y into x as pointed spaces, so little y goes to little x, and I have a covering space x tilde, little x tilde on top, when can I find the lift of f? All right. Okay, and I should say here I have to assume this. I have to assume path connectedness of y and local path connectedness. You'll see why in a second. So when does a lift exist? And the answer is, well, a lift exists if and only if the following condition holds. The push forward of the pi1 of y is contained in the push forward of the pi1 of the covering space. And okay, this maybe looks a bit mysterious a priori, but you'll see. Let's see why this makes sense. So the first observation, of course, is that if f tilde does exist, then f tilde, no, sorry, then f satisfies this formula, right? F factor, like it must factor. So f is just do f tilde first and then p. As such, the same is true for the push forwards. So f push forward is in fact p push forward applied to the push forward of f tilde. And if you look at this formula, this means, well, then the image of this must be in the image of this, right? And saying that the image of f star is contained in the image of p star is exactly this claim. All right, so the arrow going from the left to the right, we've done. And now let's look at the arrow from the right to the left. And the idea basically is that how do you construct such an f tilde? Well, there's only one thing you know how to do, which is you know how to lift paths, right, from here to here. So what we're going to do is basically we're going to use paths and try to define f tilde by lifting paths like crazy people. And the issue will be that it is only under this assumption that these paths will define f tilde nicely. Otherwise, we'll try to define f tilde and it will not be well defined. All right, so let's try to do precisely this. So the question is, you give me some y apostrophe inside of y, and what I want to define f tilde of y apostrophe, right? This is my goal. How do I go there? Well, I have to pass through paths because it's the only thing I know how to lift. So let's do that. So I'm gonna pick some gamma that connects y. So y, recall, is my favorite base pointing y to y apostrophe. Now this is a map in y. So now, I want to look at maps at paths in x because those are the ones that can be lifted to x tilde. So I apply f to them. Now let's look at the picture. So this map gamma tilde goes from y to y apostrophe. Now when I apply f, y goes to x by assumption because this is like a pointed map, and x apostrophe goes to some f y apostrophe. Great. Now what I can do is I can try to lift. And how do I do this? So I know lifts exist, and I can pick as my favorite starting point x tilde. So I lift f gamma to some f gamma tilde. This is this blue thing. And as such, this automatically provides a lift of fy apostrophe to some f0 gamma tilde of 1. And this I will call f tilde of y apostrophe. All right. So out of y tilde, let's do it again. Out of y tilde, I mapped it by f. Not only y tilde itself, but a path, because that's what I know what to lift. And out of this path, I lift it up. And this path, the lifted up map ends up somewhere. And this final point, I call it f tilde of y apostrophe. All right. Now the question is this even a definition, right? Because it might happen, what I depicted here could happen, which is that you can choose some other y apostrophe. I can choose some other gamma tilde such that maybe gamma tilde and gamma aren't even homotopic to each other, right? That could very well happen. And now when I do the same process for gamma tilde, I map to some f of gamma tilde and I lift it. Well, this is the nice situation. This is when I want to happen. I want both of them to finish at the same point, because then f tilde will be well defined if this is true for every possible gamma tilde and so on. But it could very well happen that I lift and plop, I'm ending up somewhere else. And then that's too bad, because then there's no map f tilde. So why cannot this happen? Why is it true that the picture is always like this, that it closes up? So what you can do is observe the following. So what I can do is I can look at the following loop, gamma, and then gamma tilde reverse. This is clearly a loop in y based in little y. Now this loop here, I can push forward it by f push forward. And this will yield some loop, as I write here, that is in pi1 of x based at little x. Now, and this is where the assumption comes. Now, due to the assumption, this loop is in the image of P star, because the image of F star is inside the image of P star. So that tells me that this loop, it comes from a loop upstairs, which means that, well, when I lift it, it will lift to a loop. And therefore, when I lift it, it yields exactly this picture. And since I have this picture, well, these 2 points are actually the same, right? Like the way in which I arrived here by using gamma tilde is the same as the way I arrived here by using gamma. All right, so that is the end. And what you should take from this proposition, I think, I'll try to go through it again, is that essentially the whole lift business, it's always a business about paths. And when you're trying to lift more complicated spaces than paths, you just have to rely on paths. And then, well, then, therefore, the pi1 of the spaces involved will play a role in this thing. All right. I'll try to put exercises on this as well. Hopefully, I don't know. Hopefully this video was good. I think this is the last video for this week. I will try to upload, okay, so this is the last, it's not the last video we'll be uploading, but it more or less corresponds to all the content that we should have covered this week in our physical class. So yeah, you might expect a few more videos, so we wrap up the topic of covering spaces, but you can, let's say, put those on hold, work on the exercises, and next week watch the next few ones. All right. Have a good weekend, although I guess I'll see some of you tomorrow in the exercise session.